before I start, I guess, oh, it's time. I guess I'm recording it.
It's on.
It says on there.
It's actually going out live, not just
Oh,
it's just recorded.
it's just recorded. Okay, it's out on the internet as well. Anyone can
I think so.
view the talks, can watch along at home. Cool. I guess I'll get started with part 2 so last time, what did we do? Let's do a quick reminder of what we were doing last time. Last time we constructed a 2 category of the objects of finite Neumann algebras, or really, I should be calling them tracial Neumann algebras. This is a faithful normal tracial state. If you change the trace, you change the object. Homomorphisms are bimodules. Okay, the identity bimodule is L2A, as in AA bimodule, where that L2A is using that trace. And composition is diffusion. Okay, great. And then for 2 morphisms, we did intertwiners. Of particular importance were the associator and unitars that satisfy coherence properties. Okay. Anything else to say about this? Or these intertwiners are bounded linear operators that commute with the left and right actions. And also it satisfies, but we didn't talk about it, an exchange relation. Okay, and you can, basically it's saying if I do F1 box times G1 compose F2 box times G2, it equals something else that you can make for, if these 2 things are composable, this is over the same thing. So this is over B, G1, thank you. They're both over B, and they're more, then you can write down what you think, and it's equal to the same thing. Great. So now that was the 2 category we talked about. We also talked about the unitary, or the dagger W star structure. And so what is that? That is, I have this map star from Hom H to K to Hom K to H. Okay, this is something, it's involutive. Satisfies that alpha, lambda, and rho are unitary. Satisfies, just want to make sure. There's the adjoint of the box times is the box times of the adjoints. And then also, since we can take direct sums, then the W star condition and the positivity condition are both that end A B of H is of a Neumann algebra for every H. In particular, here's the exercise. It is worth doing if this is the first time you've seen this kind of thing. It says for every intertwiner F from H to K, there exists a G in end of H such that F star circ F is G star circ G. In particular, it's positive. Okay, moreover, it's equal to 0 if and only if F is 0. All right, so this is this positivity requirement. This is an exercise, And as a hint, that exercise is called Robert's 2x2 trick. That's what I'll say. Okay, so that's I think that's the right matrix. Okay, so that's Robert's 2x2 trick. Great. So this is what we've done so far today. So we've done the 2 category and we've done 1 involution. We've done the adjoint involution on this 2 category. There's a second involution that we're going to talk about today, which is this is a second involution. It's called the conjugate. Okay, so I start with H as an AB bimodule. I can take a conjugate bimodule, which is a BA bimodule. So I define it to be the conjugate Hilbert space. Sorry, this is C. With the conjugate symbols, and I define the action I do that by acting on the left by A star and then acting on the right by B star. Okay? So this is a Hilbert space. In particular, if I multiply by lambda, some scalar lambda, then what I get is lambda. Lambda pulls out with a complex conjugate over it. Okay, so that's important to note here. But it's still a Hilbert space. I can take the linear combinations of these conjugate symbols. Okay, it's a Hilbert space, has a left B action and a right A action. Okay, so this is better than just right now I've just done this for Hilbert spaces, but we can also do this with maps too, right? So this is a functor. So F is going from H to K, which is some AB bimodular map. I get a linear map from H bar to K bar. Okay, what is it? It's C bar maps to. I just apply F to C and then I take the bar. This happens to be a linear map, and that's something worth checking. Okay, that's actually a linear map. The map which takes F to F bar is antilinear. Okay, so this is an antilinear functor. Okay, but this is actually a linear map. All right, and it's a linear map. Now it's a BA bimodular map. Okay, so you should check that that's well defined, that that's BA bimodular. Great. And now it's more than just an antilinear functor. It's an antilinear anti-tensor functor. So what does this mean? It means for every H, AB, and we're going to have K, BC, there exists an antilinear unitary. Sorry, this is actually a linear unitary. And this is going to go from nu, let's do KH. It goes from K bar, H bar, and I take these two conjugate spaces, and then it allows me to take that bar and make it one bar, okay? And what's this map here? It's just okay, and this is actually unitary. It's a unitary isomorphism. Now, it turns out this map, this is well defined because it's B middle linear, right? Anyway, you have to check that it's unitary, and that's an exercise. Now, if you want a hint on how to do that, here's the hint. Another hint is as follows. Here, I never told you the inner product on H bar. So the inner product here is just defined to be the inner product from H, but in the reverse order. Okay, that's the conjugate space has the conjugate inner product. Okay, and you can check that that's an inner product. That's whatever. So the
No bar on this one?
sorry, no bar. But I've switched. Notice that C bar appears on the right here, but it appears C appears on the left here, and that's why it's
I see.
yeah. So if you have it's going to still be linear in the left spot here.
And anti-linear on the other.
Yeah, and anti-linear on the other. Yeah. 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 Sorry, now you. Let me go home. I have to make sure everything should be okay. Great. So what you show here is that these the A-valued inner products satisfy the following. Here's the hint. It's that if I now I'm not sure if that makes sense, right? Because it should be linear on the left-hand side.
If I want to reverse the order, but then put a bar over the whole thing, right? I mean,
Yeah. You're right. I think that has to happen because it has to be linear on the left-hand side. I think you're right. I think I need that. Okay. So here's the hint of what you want to show. Really?
I think it is correct before.
I thought it was correct before. Anyway, we can easily check, right? I mean this one is linear on the right, whereas this one is
If your
linear on the
space
left.
is one dimensional.
Sorry. If your space is one-dimensional,
Then it's eta bar psi in either case.
yes, that's right. So, No,
See, then
one of them is clearly conjugate linear in the first variable, whereas the other one is, right? I mean, no, it's fine. This is linear in the first variable because let's just do it. That way there can be no, right? So if I take lambda bar, eta bar, psi bar, which is equal to, and then that's psi with lambda bar eta, which is lambda psi eta, which is lambda times eta bar psi bar. Okay, we've checked it. It's without the bar.
what does it actually say though? It's I can't see this over the writing.
The inner product of eta bar with c bar is the inner product of c with eta. This is linear on the left, conjugate linear on the right.
The
And
top
that's
one
the
has
proof.
the top one has 8 on the left. And
This has eta bar on the left,
Eta bar on the
this one
left.
has eta on the right. And it may look like, but that's the point, it's the conjugate Hilbert space. And that's the inner product. Here's the proof that it's linear on the left. So there can be no more confusion. What?
Keep them on the same side, put the bar over top.
You can keep them on the same side and put the bar over top if you want to, but I don't want to. The switching back and forth is the, anyway. So here's the hint for showing that nu is unitary. Now we can be sure that we're right when we say this hint. It's that for every, so if I have h sub b, so if I have some two vectors, c1 and c2, in here, if I take the right b-valued inner product, well, h bar has a left b action, and I can take its bounded vectors, right? And the bars are bounded vectors here. The bars are both bounded vectors here, and here I now leave them on the same side. Okay, so this is a bit tricky, and that's why I point out the hint here that you have this formula, but now they don't switch sides here. Okay? So this is an exercise, you prove this, and then you can use this to prove that that's unitary. again, the notes should have proofs of all of these statements. It will work it all out and make sure that it's right. So anything that you're worried about, you can check in the notes. Hopefully in the week to come, that should be up. Okay, great. So now I can talk about what a real structure is on a bimodule. So in a bimodule H, okay, so well, let's say that's okay. You take this A bimodule, a real structure on H is an iso, is a unitary iso. R sub A, which goes from H, R sub H to H bar, such that here we want that the condition we want is it should just anyway it should be if I do RH bar, that's a map from H bar to H bar bar, but H bar bar is just H, right? The conjugate of the conjugate is the original space back on the nose, right? Because you're just taking a complex conjugate over space, right? You can say there is an isomorphism from the bar bar symbol to the without the symbol. So you can, if you really stick where you can have this piece of extra data, but really the complex conjugate over space, if I take two complex conjugates, it's the identical thing. So RH bar is a map back to H. If I compose that with RH, right, that should just be the identity on H. All right, so that's what I mean by that. Here, yeah, great. That's a real structure. So notice now that L2A has this. I'm going to take A omega and I map it to A star omega bar. This is a linear unitary isomorphism that satisfies this equation. Now you can think about this as also, this is our map J, except this is J was our anti-linear version of this. Okay, so one way to think about these real structures is with unitaries, actual linear unitaries, and another way to do it is to think about anti-linear J's. Okay, so an isomorphism into the complex conjugate space is the same thing as an anti-linear isomorphism into the same space. Okay, that's another way you can think about it. So really I can think about linear things or anti-linear things, it's up to you, but the point is that these are the same, they're basically the same thing. Okay, and moreover, great, these news satisfy some properties. All right, so nu satisfies some coherence. Okay, what are the coherence things for nu? First of all, there's an associativity, which is a pentagon. I'm not going to write it, but you should, we had that, we looked at their fusion, and then we looked at an associator for three of them. And the point is that there's a, if I have three of these and I put these in there, it's going to be associative, and it's going to, sorry, that's not a pentagon, it's just associative, we can write down what associativity means, it's not, sorry, pentagon was for associate, right, so it's, if I do L box times K box times H, all with bars, this one is B, that's with C, there's my D, there's my A, right? Well, what do I mean by associative? I mean, one thing I could do is I can come this way, I can do that. Over here, I have C and A, I have L bar, I can do D, and then again, I can do a nu, and then this goes to, maybe it is a pentagon. Well, maybe it's a, anyway, we'll see what it is. here, or I could do the following. I could do I can associate by an alpha. I can do a new to put those together. And then I can do, it's unfortunate, it's a hexagon, right? And then I can here do, it's really quite unfortunate now. And then here, this is alpha bar now. Okay, so this is actually a hexagon, but I painted myself into a corner. Hexagon. 1, 2, 3, 4, 5, 6. All right, great. So that's one thing it satisfies, and then there's also some squares that are unitality squares, and there are two of them. But I'll write one of them. If I have H bar, I have L2A bar, down here I have H bar, L2A, up here I'm using the real structure now, get H bar box times RA, here I use new, I have L2A box times H, whole thing barred, down here I can just use my row for H bar, my unitary, I go to H bar, and then down here, this is lambda bar. Okay, that linear map, and that has to commute, and then there's another one for fusing on the right. Okay, so that's the coherence axioms for that. And then there's also, finally, you need the following. If I take I guess, Aaron, you kind of looked at me a little bit funny when I said, if I take H bar bar, it's actually H, right? You're like, well, then maybe not, you're okay with that? Okay, I was reading, I thought you were not okay with that. But the idea here is that if I do, if I take H box times K, which is H bar bar, box times K bar bar, and here I do a new, move one of these outside, and then I do another new bar. This had to be the identity. Okay, so this is all the coherence that you would want for all of this stuff, and great. So everything, this is all this coherence, and this is another. This gives you what's called an involutive structure. Another involutive structure on this 2 category. Or maybe you could say a conjugation, maybe. Which I guess I already said. Okay. You might say it's an involutive structure, it's probably easier to call it a conjugation. Now, great, what do we do with it, right? It turns out these two, so we've got this adjoint, and we have the conjugation. It turns out these things are compatible, and that's super important. Okay, so the adjoint is compatible with conjugation. What does that mean? Well, it means the following 2 things. First of all, I guess I said that this was unitary, but I didn't have to anyway. So this is this new and R. These structure maps are unitary. And the second thing that you need to show for all f going from H to K f star bar is f bar star. Okay, these 2 conjugations commute, right? So f star is a linear map. I can take its bar, I get another linear map, etc. Okay, and the map f goes to f star bar is then linear, right? Because they're conjugated twice. Yeah? So how does one prove that? We could do it, it's not so bad. I don't know, let's prove something. This is kind of an important thing. Okay, so I'm just going to take F bar, C bar, eta bar. So this is happening where? This is happening in K bar. Yeah? That's this. K bar, that's defined to be eta with FC. Okay. Okay. But now I can bring over F star. And that's with H. Then that's the same thing as C bar, F star, H bar. Now I'm in H bar. And that finally is the same thing as, just by definition, C bar, F star bar, H bar, H bar, and we win. Okay, that's it. Super easy. I probably should have just given it to you as an exercise.
Can
But
I
I
take
don't
it back and say I did look too funny, but
What?
H bar bar equals H?
You want to say that that's funny?
No, is it actually equal or just isomorphic?
Depends what you think complex conjugation of the Hilbert space is.
So H bar, I guess, probably, I mean, I guess,
It just
Like,
seems
say
like
what-
we've been very careful so far about something that equals something that, well, most things are isomorphic.
So there is, yeah, so, okay. We can say, I mean, an extra piece of data that I've actually, we can suppress it, but I can say H bar bar is the set of symbols C bar bar, such that C is in H, and then there's a natural isomorphism with C bar bar, and we're gonna call that phi sub H, and that satisfies more coherence things. And, you know, in the notes, I'll perhaps put in phi, but here I've just said they're the same. If you say complex conjugation is really like a mirror image, that's essentially what this is, and, you know, there's a way that you
Somehow
can
it's
just say,
safer to say this one's the same than saying
yeah, this is,
associativity is two things that are the same.
yes, because you can't always suppress associators. Like you can always say a tensor category is equivalent to a strict tensor category where the associators are actually identities on the nose, but like associators really are, they're non-trivial things. You can suppress them from the story and just pretend as if they weren't there, and that's fine, and that's totally okay to do, but you can make mistakes if you do this. Whereas calling complex conjugation twice the identity, you're very unlikely to. This seems like a different type of, you know, this is a much, that's a lesser grade of a lie in my eyes, yeah.
I was just gonna say, I mean, I don't remember if you told us what the symbol C bar means, but I mean, you're talking about the antilinear isomorphism to the dual space where you're every vector in the Hilbert space with
Yeah.
linear functional coming from taking the dot product. So doing that twice is sort of, I guess, trivial. That's what
Yeah,
we're
it's,
saying now.
one way you could say it is psi maps to you're just flipping back, yeah, you can do it that way too. By taking dual space. But then you are saying, then there is a natural isomorphism to the
But I think you have to sort of do that,
to the
otherwise the symbol C bar is not really, I mean, I don't know in what other sense the symbol C bar is defined, I mean.
I've just defined, like, it's complex conjugation on the,
But you want it to be antilinear, right? Because you use the fact that it's antilinear there. So, I mean, somehow you're defining it simultaneously in all vectors in Hilbert space in such a way that it's antilinear. I think implicitly you're using the dual space for that.
I can just
Well,
define for every C, a symbol of C bar such that lambda C bar over it is lambda bar C bar.
I mean, it is just H with a different product. Right?
It's just it actually, you can say it's just H with this other inner product. And in that case, then the bar of the bar is exactly the same thing, because then you've taken the same set, you put this other inner product on, and then when you go back, it's the same H, the same inner product. That's actually the best way to do it, to say it really is the identity on the nose. To even say that they're different symbols is kind of, I do it so I don't mess up. It just says that there's another inner product I'm working with, but really, that's exactly right.
I mean, so that's what obviously, I mean, so you say, and for every,
It's the same Hilbert space with a different inner product.
but you're also using a different, somehow a different, you're saying
And a
something
different
scalable,
complex
you're
structure.
saying
It's a
something-
different complex structure on that.
Yeah, I mean, I think it's the easiest way.
But it's the same set. It's the same set, but I'm thinking about the other complex structure on it.
So you just put the bar over top to remind you that you.
That you're using the other complex structure. And then if you do this twice, you get the same
But
complex
that-
structure that you
I
started
understand in
with.
what sense that's canonical. I mean, you're saying that you for every for every side in your space, you're now calling it psi bar.
Yeah.
And you're doing it in such a way that lambda times psi in the original is now lambda bar.
Psi bar. That's
Psi
the
bar.
that's
So there's
the
different complex
conjugate,
structure, different in a product.
different complex
But it's
structure.
the same psi, you just put the bar over top to remember that you're using a different.
Okay.
Yeah. So this is a way that you can say it actually is on the nose, but you're safer. I mean,
Okay,
one
that's
way
fine.
you have to talk about these, the other way you don't, and this lie is not very bad. Either way, like you can do whatever you want. Okay, so this is basically what we've shown here is that this 2 category is bi-involutive and W star. Okay, it's a W star 2 category which is bi-involutive. It has 2 involutions. They are compatible. It's W star in that, you know, all these endomorphisms of one morphisms are actual honest to God von Neumann algebras. There's an abstract notion of this, which we can do if we wanted to. I don't want to today, but basically you can just talk about an abstract category with all of this kind of stuff, and that's great. Now, why did I do all this? The whole point of doing all this was to motivate the graphical calculus and everything you can do with the graphical calculus. We still have a long ways to go to develop the actual planar algebra and all of the graphical calculus and the planar calculus that comes with the planar algebra. Okay, so I'm making a distinction here between graphical calculus and planar calculus. Planarity, I mean, these are going to be diagrams in the plane, but there are certain things that planar calculus, we want to do in a planar calculus that we don't know that we can do yet. And that's going to be a whole discussion on duality, which we'll get to. I really was hoping to get to today. This is all taking much longer than I thought it would. Oh well, okay, so what's the graphical calculus? So objects correspond to regions. So with shaded, these are like shaded regions. So maybe A is an unshaded region, B, maybe it's going to be a white shaded region. If I have a C, I'll use a yellow shaded region, or something like that. All right, so shaded regions correspond to objects. One morphisms are strings. So here, A, B means I
How
have
many
a
shades do you have?
sorry. I have all the shadings are for every Vaughan Jones algebra. There's a different shading. Okay. But this is just a basic 2 category thing. So all objects have a different shading. Okay. So the same shading means you're dealing with the same object. So here, when I write this, this is a string. So this is a you have a string for every one morphism and a 2 morphism. This is also a 2 morphism. I'm identifying the 1 morphism with the identity morphism. I'll get to that. 2 morphisms look like coupons. So if I have, say, let's do an example like this. Here's H, that's K, that's L. Okay, here this is going to be AB, this is going to be BC, and this is going to be AC. They're going to look like coupons. So by the way, these 1 morphisms are going to be, when I compose them, composition of 1 morphisms is done just by writing them next to each other. Okay, so that's H box times K. Corresponds to this. And now this is F. This is now in HOM AC from H box times K to L. Okay, so that's what this looks like. It's just some coupon.
Why do you call it a coupon?
What? Or a box. What do you want to call it? You can call it whatever you want to. Coupon is a standard term that happens in the literature. So,
What's a coupon?
a coupon? A coupon is like something like in your newspaper that you would cut out and then take it to the store to get a discount. And this is in the US. Sorry?
It doesn't look like it.
There's no discount for it.
Yeah, you don't know.
There's no discount for that.
So why do you label a region with a shading instead of just putting B there or C?
Well, A is the label. That is the shading. It's A.
Yes, so in that symbol there where you've got HK with all that shading, I can't tell which is A and which is B, so why don't you, exactly, why don't you do that instead of,
You can do that.
because the one at the top is hard to see.
Um,
But if it's a big region, you might wanna put a lot of A's.
yeah, I mean,
Just put it in one region.
yeah, but then if I look at it, it's exactly as Aaron's saying. If I'm looking here, then it's easy to see it's A, but then this diagram could be really complicated, and I'm looking at another part, and I don't remember what it is. I have to chase every time down to figure out what it is. Whereas a shading is just, it's right there. It's right there. It's apparent. You can see the scope of A from a bird's eye view.
Okay, but on a blackboard, this is
The black, yeah. So in the small enough diagrams, this is yeah. So I'm gonna do it anyway.
So it reminds me of electrical circuits.
Yeah. So or for tensor networks or things like that, that's they're using the same thing. Great. So that's the thing. Now what is?
Wait, so,
What?
the two morphisms, I mean, normally it's just F.
Goes from H to K.
Well,
So if you can't
this
write
is-
H as something
Well,
box times
something for H would be just H to K. Right? There's A. Here's B. There's an F. That would be an F in going from H to K. Here, the domain, it goes from the domain to the range, or to the codomain. The domain here is H box times K. That's what's on the bottom. It just happens to be a tensor product thing, so there happens to be this here. Okay. So now, how do I compose? So what are the two so F box times G, in this case, would be something like, what did I do? H, L, K, and M. This was what I did yesterday. So let's keep that. All right, so this is what you get by box times. And composition, if I have two composable morphisms, F compose G, depends whether you read your diagrams from bottom to top or top to bottom now. I always like to think of these as operators. They can act, right? So the first one goes on the bottom, because it's acting, you're reading bottom to top. This is the optimistic formalism. So we read bottom to top, and that would be something like this. This is, if you're going from H to K to L, if everything is an AB now, I mean, I'm not being consistent about my A's and which things are AB and which things are BC, but the shading tells you now what kind of bimodule I'm expecting them to be. And now, the coherence, the exchange relation is just, I can tensor and then stack, and that's the same thing as stacking individually and then tensoring. Okay, so there's four morphisms it's saying either way is okay. Okay, so this is this graphical calculus that you can do. Now I should tell you about involutions, because that was the point of that we've done so far. What do the involutions mean in this graphical calculus? How does it work?
So all of this applies in the abstract notion you mentioned.
Sorry?
So this presumably all applies also for the abstract notion that you headed on.
This graphical calculus is it's a calculus for the abstract notion. So if you're a category person, that's the pictures I'm about to draw are the pictures that you would draw. So the associators from now on go ahead.
Strings always go up.
No. But what I'm saying is if you want to take this and you want to figure out what morphism it is in your category, what you do is you read from bottom to top. You put everything on a different vertical line and then you kind of read from bottom to top.
Strings are oriented.
Well, kind of. We'll get to that. They're not oriented, they're co-oriented. They're framed. So there's a yeah. Okay. And that's what's going on with these two different really they're co-oriented. They're not, anyway. So okay. What was I gonna say? Oh, associators. Now there's a bunch of coherent stuff that I drew, but here there are certain things that you don't draw, because now we're going to suppress all coherence data. Here, coherence isos. Okay, and what does this mean? So we have these alpha, lambda, rho. This is, the associator. These are the unitors. Okay, we suppress these. We're going to suppress things like, so let's suppress that for now. Okay, so in particular, the identity for L2A is just written by It's nothing. It's just the two morphism is just there's nothing to nothing. Okay, it's just blank. Right? Yep.
Just a quick question. Usually when you strictify a category to get rid of the
I didn't
associator,
strictify. I'm just suppressing.
doesn't that change the underlying
it-
category?
No, it means it's there, and anytime you want to actually interpret what the diagram is, it's up to you to put them in. But the coherence tells you that any way you do it, you get the same map. Okay, so it's there, but you can ignore it, and it doesn't make any difference. We were careful in defining this thing, and then graphical calculus allows us to take all that and just shove it deep down inside and then not worry about it. But in particular examples, of course, then you really need to understand what you're doing. So the identity is just given by this. What else am I missing here? Maybe we should do an example. Well, let's just do an example so that way we're. Well, let's do an exact this kind of
Already it
example.
seems like you told us that F composed with G is two different diagrams. Right? One where you have one component which is labeled F composed with G, and one where you have two F and G. Right? So you're saying some diagrams are the same, are equivalent, even though they're different. Right?
This is one morphism. This is one diagram.
Yeah, but I think,
But you told us
I
before,
think our
you
answer
might
with
one
the
square
left-hand
might
side
F
is another
composed with
diagram.
G inside it.
It's certainly true that there are many different diagrams that give you the same maps.
So I want to kind of point out this thing that
Okay, sorry.
I want to draw maybe something like this, right? Like
Not from diagrams to morphism is not one to one. It's not a mix.
right. So here you might do, you can interpret this in many different ways. Let's do something like that. How would you interpret this? I guess the point is that the problem here is that I don't have a. Let's make it interesting. Yeah, let's do this, and then let's have something like that. Let's try that. Maybe that's interesting. Great. So here's an F, here's a G. Okay, now how do you figure out what kind of thing this is? Well, I read from the bottom upward, and I have to, the first thing looks like G box times the identity. This down here looks like the identity box times F, right? But I can't compose these without putting an associator in the middle. Okay, so really, when I write this down there, there's an associator being suppressed in the middle, so you put in the alpha, there's only one choice here, and then this turns out to be this composed with that, okay? And I'm not going to put in any labels here, but that tells you that when you're reading off things and then going back to the category, you can do manipulations here, and then you go back to the category, you have to put the associators back in order if you really want to get it right. Okay. Involutions now. What do the involutions do? Okay, so the first one was the adjunct, right? So
So what's the subscript to the identity? Just to remember.
sorry?
What's the subscript to the identity?
There's just L2A here, which you don't even draw the string for it. You don't draw a string for L2A ever. And it's just there. The point is you can put it there. The unitary, you can always, you've suppressed the unitary, so that means that you don't write it there. So for example, the unitary, which would be what, L2A box times H to H, say, right? What would that look like? Well, you have the identity morphism here. You have this thing that you don't really write anything here. You have this box here, and then you do that, right? So one way to do it is to have this lambda sub H here, and you can do it, right, by having that in there. Or you would just write, H, and then it's just there. You've just suppressed it completely, okay? So you just shove it into oblivion. And if you are worried about that kind of thing, we can talk about it later. So what's the involution? The first one is this star map. Well, this is going from K to H. This is a horizontal reflection, vertical reflection. What is it? It's a reflection about the X. Okay, it's a reflection about the x-axis. Okay, so reflections, anytime you reflect something, that's conjugate linear. Okay, so you should think about you've got You've got our world over here, and you've got the mirror world on the other side, which has the complex conjugate structure. And any time that we go to the other side of the mirror, we've done something antilinear. Okay? That's one way to think about it. And now, what's happening with, so this is adjoint. And then there's conjugation. So let's do F. And here, I'm going from H to K, A, B on this side. This maps to F bar, but it's a reflection about H bar, K bar. This is a reflection about the y-axis. Okay. Now, warning.
So your graphs are always going to be two-dimensional?
Sorry.
The graphs are...
Everything is two-dimensional because we're working with the two category. That's where that two comes in. All the pictures are two-dimensional because you have two category.
I see. So that if it becomes three-dimensional with the three category...
Three category. Yeah, so things like braided tensor categories, you're working with a three category. So anytime, yeah, the strings are, moving around in three space. Here's the warning, okay. Suppose H is an AA bimodule, and you take conjugation. You need to figure out how to, you need to figure out how to distinguish between these two things. And what this means is that you should really be co-orienting the strands. There's really a little framing that's happening on the strand here. To H. And then, F bar, if you want to think about this being as, it could be H equals H bar, right? You could have some kind of it's isomorphic to H bar in some kind of way. And you might want to be suppressing that isomorphism, that real structure, right? So this is for real, say H is real, has a real structure. And you want to suppress this isomorphism from the notation as well because you want to clean your graphical calculus. Then having this framing for F bar helps you distinguish between what happened, the F and the F bar. It's pretty good to have such a thing in there. But this is, I'm gonna kind of ignore that, but just, maybe perhaps this is where things like the three-dimensional, these 2+1 TFTs, right, coming from fusion categories. This is like kind of these framed theories are the ones coming from these spherical fusion categories, right? These, and this is kind of related to that. All right, so that's what I want to say for now about graphical calculus. With these two involutions, and by the way, the bi-involutive condition, compatibility, says these reflections commute. And that's exactly the F bar star is the F star bar, right? So it really is saying you've got a good two-dimensional graphical calculus with these reflections. So I've now finished the first day of lecture, mostly into the second day. Typically that's what happens when you do this. Now we'll talk about, let's start talking about 2-1 factors, okay? Because the idea here is to get the planar algebra. Our goal is planar algebra from a subfactor. And for this, we want something like the planar calculus. Okay? I make the distinction between planar and graphical because there are things that you might want to do in the plane, like you might want to start rotating things, right? And we don't know how to rotate yet. And to do this, we need to talk about dualizability. Okay, and to do this, what I'm going to do, now I'm going to pass to the language of 2-1 factors because the whole thing is so much easier when I want to work with 2 factors instead of finite but Neumann algebras, in the notes, I'm going to try to work in the most general case I possibly can. And in the literature, there's a great paper on dualizability by Bartels, Douglas, and Enriquez. This paper is called Dualizability and Index for Subfactors. And it does the case where it's any even Neumann algebra with finite dimensional center. Not a finite Van Neumann algebra, not a tracial Van Neumann algebra. Any even Neumann algebra with finite dimensional center is the objects they're working with. And all of their proofs are type independent. It's really a lovely paper. So dualizability and for convenience, for cheating, we'll work with 2 factors. Okay, so now I'm finally, I get to, finally doing the things that will prepare, well, these are the things that unfortunately Yasu had to do last time because I didn't get to. So what is a 2 factor? Let's go there. It's an infinite dimensional finite factor. Finite Van Neumann algebra, which is a factor. So what this means is that in a infinity as a complex vector space, it means that there's a trace, and finally, the center is 1. Okay, C times 1. So we saw an example. We had gamma, an ICC group, an infinite ICC group, not the trivial group, and then we saw that the left regular Neumann algebra was a 2 factor. Okay. Another thing that we saw in Yasu's talk was we can take the infinite tensor product of N2 of C, and we'll call this, and then you do some kind of GNS type construction, and this gives you a factor called R, which is the hyperfinite 2 factor. Okay. Great, so that's a 2 factor. What page am I on? Great, so that allows us to talk about the Neumann dimension. So if I have a left module, there's a continuous notion of dimension due to von Neumann, and it takes values, well, assuming this Hilbert space is, A is not acting degenerately, it takes values in 0 to infinity, whatever. I'll throw in 0 just to be, it could be the 0-dimensional Hilbert space, but that would be dumb. Okay, so it takes this continuous value of parameter, it's this continuous dimension, and you can realize any single one of them. Okay? And how do you do that? Well, you do this thing that Yasu said. If you take enough copies of L2A and then cut down on the right by some kind of projection, that allows you to realize everything. Really what we're using here is that trace of projection of A. If I applied that, I get the interval 0 to 1. Okay, so that's an important thing that actually tells you these are all possible. Okay, for the Van Neumann dimension of a left A module. I was going to say actually how you define it, but I'm going to skip it due to time constraints. It'll be in the notes. So here are some interesting facts that we want about this. First, it's finite if and only if A prime is 2, 1, is a 2, factor. So A prime is always a factor. It's either 2, 1 or 2 infinity. It's finite if and only if A prime is a 2, factor. It's infinite if and only if you're a 2 infinity factor.
You mean for A?
What?
H should be A.
Then AH is finite if and only if A prime is a 2, factor.
what
For what? H? A prime intersect, I mean, it's acting on B of H.
Oh, I see what you're saying.
Yeah, but you're totally right. If I say A prime, you should be, right, so A is acting on H. Okay? It's equal to infinity if and only if to infinity factor. Okay? 2, it's additive for direct sum of left A modulus. And 3, if I have A acting on the left of H, but it happens to have a right B action, so now A and B are 2-1 factors, okay, well, this is the same thing as the product. Okay, so it's additive for direct sum, it's multiplicative for fusion. Okay, so these are the important facts that we'll need in what follows. Great. So it's called. So let's do some. Now we can talk about index for subfactors. A subfactor is A containing B, both factors. And it's a unital inclusion, right? So 1 sub A is 1 sub B, right? And a 2-1 subfactor, that's what, they're both 2-1. Okay, so you have this trace. Now, here's a fact. I guess I'll put it right over here. Fact, the trace on a 2-1 factor is unique. So if I take trace B and I restrict it to A, I get the trace on A. Okay, so that's a fact. For finite Neumann algebras, if you picked the wrong trace on the bottom guy, you are sunk. Okay, there's no reason why it would restrict to the other trace. You're just working with finite Neumann algebras, and so that really is one big difference why I want to pass down to 2-1 factors now.
Sorry, maybe I missed. What's the purpose of just the notation with dash after the A?
It's the left of a Neumann dimension.
Oh,
Now,
okay.
what I can do is I can have a bimodule, and I have two, right? I have two Von Neumann algebras acting, one on either side, and I can talk about the left dimension, and I can talk about the right dimension. So in particular, I could talk about, if I have a bimodule for 2-1 factors, well, I could talk about dim A, H, and I could talk about dim B, H, right, which is equal to, what is this? This is actually dim of B op on the left of H, right? Because really, B op is acting on H on the left, right? But I can talk about both of those, and I'd rather have the A dash because it's acting on the left, and then B, the dash B, is acting on the right. I guess I should have given some. Anyway, if these are both finite, this is a nice condition we call H. Maybe it would then be called bifinite. Okay, so since I have it written up, let's use it. Let's not waste what I've written on the board. Okay, I've got this 2-1 subfactor. Now the definition of the index. This is the Jones index. This is the left dimension of L2B as a left A module. Okay, so I've got this I've got L2B, it's a B bimodule, B in particular acts on the left, and so this is the same definition as Yasu gave yesterday for index for subfactors. Here are some examples. First, I'm just going to review what, if I take R, tensor N as C, and I look inside, I look at R, that was N squared, I can take a cross product by a group. This is a different, this is basically, this example is dual to what Yasu said. Here, this is the size of the group G. This is the same thing as this 6 points. If I've got this outer action. 3, if I have a subgroup, okay, so here these G's are countable groups here, and that's for subgroups. And I think that's my time, so I'll stop there, and next time we'll go further into dualizability and subfactors.
Are there any more questions or comments?
You have this interaction of this finite group G and R. Does the subfactor you get depend on the action itself or just on G?
Well, if the group is finite, there's a unique action of that finite group on type of energy one factor. That's Jones' thesis, right? So what was the question was, does the subfactor depend on the action? No. There's only one. Because I'm using R,
Only one.
hyperfinite, right? R is the hyperfinite term.
So only one of what?
Up to, well, let's talk about it later. I don't want to say it wrong while I'm on the being recorded. Yes.
What do you mean by H less than G?
Subgroup.
Inclusion.
Yeah, subgroup of G. Yeah, typically, subgroups are written with less than or equal to instead of contain. I don't know why. They distinguish it from a subset. I don't know.
Okay, so shall we have some tea and then carry on? Thank you very much. Thank you.